How about this time?
Yes.
Yes, this is what.
Perfect.
Oh, okay, cool. That's great. Thank you all for the help, and I'm glad to be here. I know it's pretty early morning in Europe, and you know, recently I moved my lab from US to China. So this where I am now. I worked in UC Davis for 15 years, and I recently moved my lab from east of the Pacific Ocean to the west of the Pacific Ocean to Suzhou. It's pretty symmetric to California, across the ocean. And this is a new campus we're building in Suzhou. It's part of the new expansion of the University of Science and Technology of China. And they extended the new campus in Suzhou, where is actually the Center of Medical Device and Instrumentation in China. So I'm located in the School of Advanced Research. My lab is primarily working on two directions, and one is on the tactile intelligence, which actually I will spend most of the time of today to introduce some of the interesting and exciting progress in that direction. We study the material, the devices, and the whole system, and trying to figure out some appropriate applications, including the artificial skins and the wearable health. And then we're also trying to integrate it with some miniaturized medical devices like catheters and the smart pills. And with the equipped tactile intelligence, we use this kind of information to try to provide doctors with additional diagnostic information. On the other part, we also work on this microfluidic intelligence. So building on the understanding and the process of making small droplets, and we can make microfluidic more automated and working smoothly and seamlessly with the robotics. And we can actually doing the microscopic reactions, very digitized droplet inside. So we are able to read out the reactions and getting the analytical result in the kind of microscopic intelligence as well. So we're trying to move in either direction, one way towards information technology with our building sensors and the tactile intelligence. On the other hand, we are also very interested, making the microfluidic and the diagnostic part towards the biological, technology. So which are two frontiers of the engineering and the science, advances. So this is one of the photos I usually to, display as my first slides. This, defines, if some of you recognize, this is some of the piece we digged out from 3,000 years ago. The Asian people in the Middle East made for a prosthetic toe. And if you look at the process from 3,000 years ago, it actually not only defines how fine the quality of the system they have built that time, and how elegant the wearable device could be even through the 3,000 years of time. So if you look at the punch, the holes, and the curvature, and how real this kind of toes looks like, so it's amazing. That's actually gave all the biomedical engineer a sort of like gold standard. What you like to build is something will last a long, long time and still elegant and nice and workable. So if we look at the modern, trend for the bioinstrumentation, and particularly in the field of medical instrumentation, so we found actually quite an interesting trend in a very, very generic way. If you look at what we're working on, is we're working on towards something really, really huge, right? So all the, scanning equipment, like an MRI or PET scan, and they're occupying the whole room, and we're able to provide the whole body level scanning, from organ to organ. and it's magic, and but the footprint is also gigantic as well. On the other hand, you can see the medical instrumentation from the surgical side. We're driving towards making it smaller and smaller and smaller. Sometimes, this very small, tiny wires, the guide wires get into people's body and navigate, go to the right position and perform some surgical performance and provide the diagnostic information and the imaging capacity as well. So if you look at that, there are automation, there are intelligent, there are miniaturization, and eventually receive a minimum invasive outcome of the clinical evaluation. So if we look down to the smaller instrument we're talking about, so there are several very, very interesting new characteristics coming out of the recent development. One, what we call is imperceptible. So if you think about the wearable, is one kind of imperceptible where people put on your body and it's like a natural clothing or natural accessory put on your body and you are not able to see them as a traditional medical instrumentation. Sometimes you can also think about the implantation is a new way, but today the implantation is also driving down to a very, very miniaturized footprint as well. And as the maturation of the smart POs, today you can see the ingestible sensors become more and more popular. The smart PO has already brought a new page of diagnosis. So you can use a very miniaturized imaging pill and swallow, and it tracks all the imaging information through your endoscopic tract and provides you a whole scan of that. And as well, one thing you like to do is at one time for diagnostic purpose or surgical purpose, you like to do as much as possible, right? The integration. So we like to integrate multiple functions and multiple capacities into one devices and perform everything in one invasive procedures. One thing I'm very particularly interested is the tactile intelligence. So if you hear everything about artificial intelligence, people probably will tell you the smart speakers or the visual scanning, the artificial vision. So those are pretty mature technology. And this represents the people's eye and people's ear. However, if you think about another organ, we are having a lot of sensory organs spread out of our body is tactile sensation, right? So when do we need a tactile sensation? So at the moment we discover the electricity, and the first thing you like to control is the way how the electricity has been delivered. So remember, Franklin was handling the night in a thundering night. So one of the things is when the lightning catch up on the light, so it generates a very high voltage, and that voltage can usually kill people. So you need a switch to control that electricity to be passed through the electrical wire. So since then, we have developed a lot of human-machine interface to control the electricity and later to enable more information about the human biometrics, as well as providing a tactile control or the touch control between human and the electronic equipment. So that includes the recent advances of the touch screen and the wearable devices, the biometric devices, as well as the robotic skin. But there's a challenge, right? So the reason why the artificial vision and the artificial the sound could provide more advanced and widespread than the tactile intelligence. The reason is the artificial vision and the artificial sound, they are transmitted in a media through a non-contact way. However, the tactile intelligence is a contact method of putting the information exchanged. So it requires the human interface will be compatible with the machine interface. So now is the problem, right? So our body surface is tender, it's soft, it's it's very gentle. But if you look at today's electronics and all the computers, they are basically in, hard, cold, rigid format, which is not compatible with second to second transferring of information. We developed something like keyboard and other things. In the medical side, we have directed those into a wearable format, but it's traditional wearable format. I have a chest band put on a baby who has to be in a incubator, or we have this finger clips put in your oxygenmeters and read your pulse oximetry. And we also have some the machine band and help you to translate the motions from the prosthetic devices to the limbs which got injured. And there are many things people have tried, but so far the most tried industrial version still not solving the hard and soft interface between the human being and the equipment. So the recent trend is provide the smart wearable systems and try to extend the capacity from the diagnostic side to the therapeutic side. So they are divided into different sections, like chemical sensors. For example, the Abbott lab has this continuous glucose measurement system, which can be wear for 2 weeks without taking it out. So it measures the glucose level continuously. So people don't need to have the finger prick for occasionally, which it's kind of painful for the patient. Of course, the ECG band, which has already been incorporated in a lot of sports apparel, so that will embed some fabric-based electrode, will be continuously recording the heart rate and some other signals related to the heart rate signal. And also optical signal can be read the oxygen level, which can be particularly important for the respiratory disease patient like COVID. Mechanical sensors will allow you to record your pulse waveform, which will reflect the whole picture of the cardiovascular system. So for the mechanical sensor side, people also tended a couple, ways based on the classic measurement principle. For example, like Jonas Bau's group in Stanford has been working on the capacitive sensor for many years, and they have made the capacitive sensors ultra sensitive. And there are also multiple groups working on the resistive sensors, using the printed electronics to making resistive sensors to be very sensitive, and it can be attached to the various part of the body. We're able to transmit the signals from the body to the electronic device and monitor all the vital signals. The recent interest actually into the piezoelectric devices allows you to make the flexible sensor as a capacitive and resistive sensor, but also provide the highest sensitivity on the device level. They are able to catch a very tiny movement. At the same time, because the piezoelectric sensors are able to generate some level of electricity, they are also have the interest of combined the electrical generation as the sensing signals to be able to develop something self-powered device for the continuous monitoring. So in our group, what we are actually interested in is a new type of sensing mechanism. It's called the FITS. So FITS stands for flexible iontronic sensing. So it's originated from this lotus effect. So we know lotus has been sacred flowers in Asian cultures and for thousands of years. One of the things is very striking is when they have a droplet stay on the surface and under a mechanical small disruption, it will form the unstable state will be moving around. So a lot of chemists and actually the first discovery was coming from the German botanist Bartlow in 1977, and he looked at those kind of small tiny structures and see how and why the water stay unstable on the lotus leaf. But we're thinking another aspect of it, because when the droplet is sitting on the lotus leaf, they're unstable. So with a small mechanical disruption, the shape of the drop can change quickly, but this change also can come back when the mechanical force has been removed. So in 2011, we actually tried one effort is actually incorporating a droplet in a two conductive surface. And between these two surfaces, the droplet is forming, kind of self-contracted shape. And when you actually apply a pressure, this drop will be expanded like a pancake shape. But when you remove the pressure, it comes back. So this actually changes, instead of the distance between the two electrodes, rather it actually changes the contact area between the liquid and the conductive electrode surface. And this surface, if you know in the electrochemistry, is known as called the electrical double layer. Electric double layer known to have very, very, very high unit area capacitance, and it's ultra high capacitance interface. And this capacitance is, on a level is significantly greater than the traditional capacitive interface. Because if you look down to the equation, right, the capacitance is inversely proportional to the distance between the two charges. So in the EDL layer, this separation between the ion and the electron, so which we call Irontronic, is on the order of Armstrong. So in the traditional interface, that if we consider the MEMS type of capacitive sensor, the parallel plate is separated on order of tens of micrometer. So now you can see the capacitive level is increased by an order of magnitude of 4. So it's a significant increase, a 10,000 times increase in the sensitivity. Another very interesting aspect of this type of sensing, today we call Irontronic sensing, is the Irontronic sensing actually is not completely capacitive, but not also completely resistive. So it does have a capacitive element of the interfacial capacitance, which is EDL generated, and also because the materials stay in the on the electrode side. Today we call ion node, and it's a resistive base. So it also have a resistor. And when you actually press this device, what you can see is the capacitance increases, but at the same time, because the distance decreases and the cross-sectional area increases, the R actually also decreases. So if you know in a circuit, RC circuit, the C and R keep a constant. So basically it forms filter. So it actually is a self-filtering device. Okay, so that's why it's actually later on we found this it's a unique advantage, allow it to be able to filter out a lot of noise. So we spent the last 10 years has been working on this Irontronic sensors from original shapes, very transparent and the droplet format into the film format, microstructure, nanostructure with all kinds of different mechanisms, use of fiber shape, droplet shape, microstructure shape to various applications. And recently our interest is focused on the medical applications. So this one actually shows a little bit the difference between the capacitive, resistive, and the piezoelectric sensors. And one of the unique thing is the Irontronic sensor provides the highest sensitivity, but lowest kind of cost, because it only requires on the order of nanometer of the coating to provide ultra high sensitivity, which is on the same level as piezoelectricity. So another very interesting thing is that the Irontronic sensor is the only one keep the transparency. Okay, all the other sensors has one type of colors, but the Irontronic sensor is born with transparency, which probably later can be easily integrated with the visual intelligence as well. So if you can see this picture, on the left top corner, the first sensors we made, batch of them, and you can see particularly in order for you to see them, I have to dye those kind of droplet sensors with a colored fluid in the middle, so you can see them dyed into different colors. Later, we were able to print them into a large array, and we found that the droplet still has some drawbacks. So we are looking for the material can be easily, coated or printed on the surface. We're able later to make a, large coding on the, bigger array format. And later we're able to even to adapt the material into various material substrate and, into many different things. So we have been, overcome many of the material and processing hurdles to be able to use this material into different scenarios. So in particularly, we are interested in many kind of pressures. For example, we had the pressure taken off on the measured on the glass format, and we're able to provide the sensors on the prosthetic lamps, which are able to read something like the Blair letters for the blind people, and we're able to incorporating into the medical devices and track the pressures in the limbs and on the back in various places, also as well as the intraocular pressures. And we are able to also getting the array format to analyze the cardiovascular events and other things. So here are some simple demos. This is one of the early demo we built in 2014. And you can see this tiny droplet-based sensors are vibrating with your cardiovascular forms, and that converted from the cardiovascular signal into the blood pulses and getting you the waveforms you like to keep tracking of. On the bottom, we're able to also building the sensors in the writing papers. When you are doing the catograph, old Chinese fashion, you're able to detect from the pen, the pressure of the pen, which is made by the hairs of the animal, and with a very, very gentle pressure, and you're able to distinguish the pressure distribution throughout the writing process. And on the right top corner, it's one of the fabric sensor we made very early on. You can see it's coated on a regular fabric. By adding 2 electrodes, we're able to record the signal in a very high resolution format, but also have very, very low motion noise. So it also provided very timely responses. On the bottom actually is a prosthetic finger will be able to read the Blair letters in a format using the scanning mode, which give you a letter of hello. So on the medical side, what we're interested in is actually figure out the diagnostic information from the pulse. And you have seen this video just right now, and you can see the tiny drops are tracking the vibration from the skin, the skin vibration, generated by arterial pulse forms will be able to translate the capacitive signal, and we're able to record them into waveform. So one of the things that actually we're doing is now, because we can taking multiple sites on the rest, we're able to calculate many more parameters like the arterial augmented index and the stiffness level of the blood vessel. We're able to calculate the blood pressure in a continuous format. This actually is be able to process in a very gentle pressure compressed way, but at the same time provide you the continuous monitoring of somebody's blood pressure level. So this actually is a very interesting progress we have made recently. Another thing is that we are able to integrate the things into one of the very nice sneakers. One of the things actually the sneaker provides is you actually have blood vessel, very strong blood vessel, the pedal artery on the backside of the foot, along with multiple tendon around it. So having an array of this very flexible fit sensors around the foot, we're not only able to getting the movement of individual tendons, but at the same time get the cardiovascular information resolved. So here is actually the cardiovascular signal we resolved. We can see the blood pulses. So this blue pulses are the heart pulse, and the orange pulse is a pulse actually taken from the respiratory waves. So basically, you're not only monitoring the heart rate or pulse rate, but at the same time, you're also monitoring respiratory rate. So we compared our measurement between the pulse measurement and the ECG, and we can see there's a very, very high correlation because the pedal pulse is very strong and very easy to detect. The very interesting thing is that actually in the foot, you do have a tiny pressure you always apply. That's basically through your shoelace. You apply it between 10 to 20 millimeter mercury of pressure in the shoes to be able to wear the shoes. And that pressure is just about the right level to provide you a continuous and a very nice pulsation level from the tactile sensors we build in the insole of the shoes. On the other hand, we're able to look at the sensor distribution from the foot, and there are multiple sensors along the pedal side, and each of them were able to track the muscle tendon movement, and this muscle tendon movement were converted into machine learning algorithm, and with this process, we're able to do all the movement, and we're doing the gesture recognition, and from that we can tell you your gesture and the status of the whole body, and that give you the whole picture of the human status during the daily activities. So we use that to train CNN network, and that will yield a very high cross model model to be able to tell you not only how many steps you walked, we're knowing you are standing because you have a high pressure in your shoes, or you're sitting, or you're walking, you go to upstairs, you're downstairs, you have different walking patterns, and the sensor groups inside of the shoes, it will resolve all the information you have. So this provides you a very interesting picture of different devices. This is one of the things we build later on, use the shoes, and you actually can see we have 5 sensors building the shoes. Each of the shoes has the sensor array inside. This will also allow you to track the people's responses at the same times to do all the activity level tracking and resolve your body information and everything. So this shoes actually has received Innovation Award in 2019, and in 2020 it received the FDA approval. Right now we are working with one of the company to develop wearables for the Parkinson patient. So we're able to track their vital signal at the same time we can know how well they are in terms of the walking and daily activities and their neural past walking patterns as well. Another one is that we're actually building this tech glasses which are able to read your pulse from your head. One of the actually challenge to building the wearables on the glasses side is actually glass only have 4 contact points. You can see it's there are 2 contact points on the legs of the glasses and 2 contact points near your nose of the glasses. So the interesting part is this 4 contact point responded to the few muscles, right? So on the leg side, you're actually looking at the superficial temporal arteries. On the facial side, you are actually in contact with the orbital oculi muscles. So each resolves different information. One is resolving the blinking features. So the oculi muscles actually provide you the blink rate, blink interval, and blink durations. But the superficial temporal arteries provide you the piezoelectric signal and the supratemporal arteries. So that provides you the
you just have about a minute left.
Okay, sure. So I mean, then you can actually diagnose both the eye blinking information as well as your other information. So this actually combined, you're able to join these 2 information together to resolve something like a fatigue or non-fatigue or coughing and other things to detect it from the human body. So we have this very interesting, glasses to be able to resolve the information from the patient. So this is actually something very simple. You can put on, you're able to detect. Okay, so we got pretty high level of medical precision. You can see we can able to derive this model for training people dry eye and health people, and we can also do the fatigue and non-fatigue mode for different patients. So I think I probably have to skip the last one, but I'm happy to answer any questions you may have, for this kind of flexible wearable sensing for the future wearable, and how we can, catch up the diagnostic information in a or imperceptible ways. You can, read the biological signal from the real wearable format. Thank you.
Thank you, Tingrui. It was really impressive. Thank you very much. Very good start of the day, and you have really beautiful slides. Any really pending questions? Yeah, you have only 1 minute left from the audience. If not, please direct your questions directly in the chat. And Tingrui, can you give your details in the chat as well, so that people can direct their questions directly to you? Is that fine?
Okay, sure. So I'm just stopping the share, right?
Yes, please. Yes, please.
Okay. Thank you. And
thank you. Okay. And from our side, we continue with the second talk, which is from